Hi, my name is Ben Freireich. I'm the Technical Director at Particulate Solid Research Incorporated, PSRI. And today I'm here interviewing our guest speaker for plenary at the 8th World Congress on Particle Technology, Jinghai Li. Jinghai Li is the National Science Center Foundation of China's president, and he's giving a talk on Mesoscience, opening a new paradigm of particle technology. So thank you for coming, Jinghai.
Yeah, glad to see you, and it is my great pleasure to discuss with you the topic of the concept of Mesoscience, and also all of the AIChE audience.
Excellent. Excellent. So could you enlighten the AIChE audience a bit about Mesoscience and the prominence of mesoscale phenomena?
Okay, let me explain.
Excellent.
Little bit. Okay, when we study problems, in fact, naturally, we study a system. Yeah.
Yes.
And in the system, there is huge number of elements or units. Yeah. So we call the element scale and we call the system scale. We know very well. But in between, there are a very complicated structure, dynamic and heterogeneous.
Yes.
So that called mesoscale structure or mesoscale phenomenon. Very complicated. And the mesoscale structure is, of course, related to the element scale interaction. But it is also critical for the performance of the system.
Yes.
So that gives really very important significant. That gives the importance of studying the mesoscale structure.
So I'm familiar with your previous research in EMMS and the mesoscale structures being clusters.
Oh yes.
Are you extending this idea to other areas of particle technology?
Okay, let me explain a little bit.
Okay, cool.
You know, in particle technology, we are working in two steps. First step, we should know how to synthesize the particles, materials. The second step is how to produce massively the particle materials. And the first step, we know the molecules, and we try to assemble huge number of molecules into particles. So the structure is critical to the assembly of structures. So that's in this case, molecular is element scale and particle is system scale.
Yep.
But in between, the assembly of molecular is mesoscale.
That's right.
Very complicated.
Okay.
And then we have the second step to produce huge number of particles, huge mass of particles massively. So in that case, the particle is element scale and the reactor is a system scale. But in between, the particles interact with each other and move behavior collectively. So that gives, again, very complicated mesoscale structure. So that's two levels of mesoscale structure. Very complicated. The first is a challenge for chemists and material scientists, and the second for chemical engineers.
For process engineering.
For processing. But fortunately, recently, we recognize different mesoscale structure maybe follows the same common principle.
Okay.
So that is why we propose the concept of mesoscience.
What is an example of one of the common features, let's say, between those two?
Okay, that's the second problem.
Okay.
Second question. Okay. Let me explain.
Yes.
Explain what. You know, let's come back for this figure. You know, it's different elements interact with each other. Yeah? And in the system, we have so many elements. The mesoscale structure could operate in 3 different regimes. Yeah? So in the extreme regime, maybe only one mechanism dominating.
Yes.
Yeah? And another extreme regime, maybe another mechanism dominating,
Right.
A or the B.
That's right.
But for these 2 cases, the structure is simple. Yeah? Structure is also simple. Yeah? There's no complexity. Yeah? But if A and B plays roles or dominate this jointly, that gives very complicated structure. So we study this regime, not these 2 extreme regime. So that means when we have 2 dominant mechanisms, we have very complicated mesoscale structure.
Yes.
So the mesoscience is not only for scale, mesoscale, but also for regime. Yeah?
Mm-hmm.
The meso regime.
Right.
Meso regime. So that's the whole concept.
So you're saying
mesoscience.
mesoscale initially is I have the, let's say, one microscopic scale, I have a
Yeah.
scale between.
Yeah.
But also in one of each of these I could have a dominant mechanism.
Oh yes.
Dominant mechanism,
Yes.
but the mesoscale tells me that both those mechanisms are happening
Oh
simultaneously.
yeah. You're fully right.
Excellent.
Yeah.
Okay.
So even in the mesoscale, if only one dominant mechanism, the structure is simple. But only when 2 dominant mechanisms plays role, structure is complicated and dynamic. So that's mesoscience. What mesoscience is devoted to.
I understand.
Yeah.
I understand. So
Yeah.
in regard to the talk that you're giving,
Yeah.
what are the key insights you'd like the audience to take away from the talk?
Oh, okay. For instance, for chemical engineering, we study the material diffusion and reaction. Yeah.
Yes.
If the process is dominated only by diffusion, the reaction is simple. And if the system is dominated just by reaction, the structure is also simple. But most cases, we have both diffusion and reaction plays joint roles. That gives complexity. So we must use the concept of mesoscience to study such a very complicated structure. Yeah. For instance, turbulence, I gave you another example for turbulence. If the viscosity effect dominates, that gives laminar flow, very simple. If the inertia dominates fully, that also gives not so very complicated structure. But when both viscosity effect and inertial effect, they interact with each other or compromise in competition, that gives the turbulence. So that is turbulence.
Inarguably very complicated.
Oh, yeah, very complicated. Very complicated. So we have many different examples. For instance, fluidization. If particle dominate, that is fixed band. Yeah?
Right.
If gas dominate, that is dilute transport. Yeah?
Yes.
But for fluidization, neither particle and nor the fluid could dominate. They have to compromise in competition.
Right.
That gives complexity. So that's the reason why fluidization is so complicated.
It's complexity that keeps us employed.
Oh yeah.
That's right.
So we should, in this case, I mean, if 2 dominant mechanisms exist in this process, we have to, the traditional series is not sufficient. So that is why we proposed Mesoscience to deal with such complexity.
I'm convinced.
Yeah. Okay. Thank you. Thank you. I'm glad to.
Go ahead.
Yeah. So many challenging issues is operated in the mesoscale and mesoregimes. So we should looking for the common principles. So that will give us the possibilities to solve many global challenges. For instance, we apply computational fluid dynamics. Yeah, you are familiar with. Yeah, and in the grid, yeah, there's structure, but the traditional approach just made assumption that in the grid it is uniform, but that is not sufficient, not accurate. And so we should consider the structure, mesoscale structure in the grid. So that gives the possibilities to upgrade our simulation, CFD simulation. So the common principle, we recognize the common principles for all of mesoscale structures. That is, in physics, the compromise in competition between different dominant mechanisms. That's the physical principle. And in mathematics, such a principle could be formulated as a multi-objective variational properties, not single. So the traditional approach just to try to looking for just a single objective variational property, but very difficult. And different from the traditional approach, Mesoscience proposed to looking for the variational principles, not single, but we're looking for multiple variational principles, variational criteria, and studied the interaction and the compromise in competition between them. So that is much easier than directly looking for a single one. Yeah. So that's something different from the traditional circles.
Yeah. That's something that people will have to get used to thinking of.
Oh yes. But it's not so easy.
Right.
It's people. The thinking has momentum. Yeah? And it's not so easy to change.
Yes.
Not so to come back. They are looking for a single one. It's not so easy to come back to looking for the double, 2, 1, or even more. Yeah? Not so easy. So I hope our talking could help the people, convince the people, understand a little bit. Yeah.
Yes.
Yeah. To change, to switch the thinking way. If we could make progress on Mesoscience, that gives possibility to solve the mesoscale structure. That means we establish the relationship between element and the system. So that is, in fact, we know the logic of the interaction in the systems. And if we know the logic, we can establish the mathematical model, and we can establish the software and also computer in the same logic.
Yes.
So that gives the highest, not highest, much more efficient computation. So it is very important. And if we have sufficient accuracy, we have sufficient speed, and we have high efficiency of computation, and we will realize the real-time simulation and realize virtual reality of chemical engineering.
Well, that is an exciting future.
Yeah.
Well, thank you very much.
Yeah.
I look forward to seeing the rest of your talk and reading more about Mesoscience for sure, mesoscale. And I'd like to thank you for sharing your perspective on Mesoscience and particle technology with us. And thank you for coming to the World Congress of Particle Technology and speaking.
Yeah, thank you. Thank you very much.
Thank you very much.